Alright, time for another draftphysics.com, debatephysics.com also, but nobody to debate, unfortunately. So, can't find anybody who can man up and show up for the debate. So, I'll make this an update video, and then I'll talk a little bit about levers, and then about the difference between elastic and inelastic, and just the simple argument that really all you're doing is following the energy, and it always goes somewhere. You know, conservation of the motion. The motion is always conserved. It's just changed from being in a big thing to being in little things, and it goes from being in little things to being in big things, and that's all it can do. But anyway, we'll get to that after. We'll do this first. So we'll go back to a couple of air track videos. You know, Brenda Toblin, and you know, I don't know if I need to click on that one actually, but I will, just to show the image of it. Won't bother playing it, but I mean, you really can tell if you use her numbers that it really does work. And so I think that's what this video really was, but who knows. Oh, that's a big jump. That's not, this is supposed to move. Okay, it went back to the top for some reason. So, yeah, so I guess when you're, yeah, it goes to a new page, so it starts off at the top again. Okay, so that's the catch. All right, so this is where I wanted to be. All right, so, draft, energy storage in transverse collision. So that was sort of getting to the point that's what the difference the spring makes. And so I did some explaining of that, and explaining how it does matter which way the energy is going. So it's sort of important in terms of the relativity argument, and that's what I talked a little bit about in that video, is that it's sort of a debunk of relativity. Because the idea is, okay, they always do these relativity scenarios pretending that you can't see the rest of the universe to see which way it's moving, to tell how much you're moving. This sort of relates to some idiot who left a comment because, what's his name? Bill Gates was talking about the fact that the moon doesn't rotate. Well, everything that sees the universe, you know, the stars, if the stars move, then you're rotating. You know, that would be the standard. It's the external universe that we're assuming isn't moving. And it certainly wouldn't be likely that it's swirling, you know, and the moon is really stationary, that the moon is the center of the universe. So you really have to judge that stuff by the external world. Well, the point is anyway, you could have two trains passing each other, and they could just stick a little ball on a little spring, and the two balls could hit each other. And the fact is, depending on which train is moving, the balls will react differently, as long as they're different masses. So as long as one of them's twice as big as the other ball, you can sort of guarantee that it'll tell you which one is moving, because the energy transfer will be different if the small object has the motion and hits the big object versus the big object having the motion and hitting the small object. And so it sort of does debunk this, the fairy tale kind of relativity where they try to say nothing's really moving, or, you know, that kind of nonsense. It really isn't consistent with the facts. So anyway, that's more than I wanted to say about that, but anyway, that's what you get. Alright, so yeah, I have to go back down again. I have to figure out how to do that with less weight. So then I did a junk comment video. There's no point in wasting time on that. So your logic, this one was about, let's see. Yeah, this was about again, the transfers, and the fact is that you can get the energy back in these scenarios where you drop a mass onto some other object and they both have to move, and you can kind of understand that it moves half the speed because it's got to share its momentum with another mass that weighs the same amount as it does, so it has to share its momentum. And that if you launch the object back out, that is, you stopped it from moving, you put it back to being neutral, that the energy this would gain would put it right back to the same speed it lost. So it would be completely conserved, so nothing was destroyed. You know, it's perfectly consistent with momentum being a rational way of looking at the universe. Perfectly consistent. All right, so I think that's the, yeah, your logic one. And then so I did a draft on motion and drag that just points out this whole argument that it's the first motion. You know, if you turn left and then you turn right to compensate, right? The turning the opposite way is a reaction. okay, to the initial action. So you could argue that if you had an actual left, and then it went right, and then it'll go left again, and it'll go right, and left will always be one ahead of right. You'll always have one more left, and then you'll have right in the sequence. And so it's sort of an argument for what actually real motion would look like in the small universe, which is the only universe. So if you understand that concept, that the small universe is really the only universe, yeah, then it's pretty easy to understand. Okay, then I did another Brozo video, again, arguing about doing an inferior experiment. You know, I did the roll little balls down a track because I didn't have an air track. So if you have an air track, then you can just launch them into the same, and it's not a problem. But I didn't have that, so I didn't do that. But frankly, it's, in my opinion, it's just not a viable argument for somebody to attempt to argue that twice the mass doesn't tend to move half the velocity. It's such a standard, and that's what I'll talk about with the lever in a moment or two. So anyway, then I did a response to Piro's math. I can't say it was a great video because you know, it's just you're just dealing with the fact that they keep forcing the argument to be about distance when the argument is about time. And I think it can be demonstrated in every single gravitational scenario you can create, that all you really need to know is how long was something in the gravity, especially free falling in the gravity, and that'll define how much energy it collects, and that it's all about time. It's all about collecting the gravity. The fact that gravity is basically a consequence of there being more energy coming from the outside than coming from the inside. The floor is producing less of something than the atmosphere is, and therefore you are just merely pushed by the stream. And that logic works. That there isn't any experiment that will prove that logic to be insufficient. Alright, then we have more air track stuff. So that was yesterday's video. Oh, I probably missed something. Yeah. Alright. Yeah, that's junk comments. Brozo. Yeah, I already did that. There's the math one. Okay, so this was the next one. Physics doesn't work. Oh, that was the perpetual motion machine. So again, I'd really like somebody to explain if the Lewin experiment is a fact and you can create extra momentum and it's not a problem. I'm saying this is the consequence of it, that I can easily make a free energy machine and you know, create free energy. So if Lewin's experiment is the truth, explain why this machine wouldn't work. But no one's offered any explanation. So we don't have that. Alright. Then there's more junky comments and physics versus more air track stuff. So this just got into you know, the fact that the frame rates aren't really good enough because they're a little bit inconsistent. But you know, you can account for that, and you can say, well, if every fourth frame is twice as big as the other frames, and the other frames are 2s, then you can say, well, it averages out to 2.5 or 2.4 or something like that. So it can be useful, but you have to do a little more thinking to get the right answer, and there aren't too many people willing to do that little extra thinking. So then this one was just more you know, verification of the air track, and you know, how you rationally analyze what you're seeing. And then I did Brozo posted 10 comments on a video, and so I read some of the crazy comments. I mean, they're actually crazy, so silly. It's incomprehensible. A rational person can't understand what the fuck he's talking about. He says he proved it, he's done the experiment, and yet he won't show the proof. It doesn't make any sense at all. Alright, so on to better things. So what do I need to hit here? I believe I will gracefully exit that and gracefully enter this. Alright, so here's the, again, I mean, I've done this lever argument, but you know, it's always a little, you know, less than perfect in terms of how I'm making the argument, so I'll try to make it as understandable as possible. I don't know why that camera looks like it's going uphill, but whatever. All right, so you just have a simple device, a lever, and so it pivots on this point. And I think people could agree that if I put equal mass, equal distance, okay, that I can expect, all right, not only that it will balance, but that it will oscillate consistently, and that if I do drop this object here, that I will lift this object an equal distance. So the simple argument being made is that if I put a half mass out here, so let's pretend this isn't here, and then I do the same thing, they somehow don't think the same result's going to take place, in the sense that this will get the same energy that this has, and that means it's half the mass. It'll go, you know, it will be launched at twice the velocity. Okay, so whatever this v is, this will be v times 2, okay, of this lifting up. Now the logic is so simple that you can't deny it, really, because all this object is saying is that it's like this object could still be there. When this one's here, you could just fool it by saying, well, I'm just going to put this one here, because it can't see these two as being different. You have to understand, when this comes down, all it's going to notice is that it moved this part of the lever that distance. It's not going to notice that it lifted this part of the lever twice as high. So this part of the lever is moving, you know, this much, and this part of the lever is only moving, I'll draw it down here, you know, this much. So this is moving twice as much as this is moving. But from this perspective, twice as much with the lighter object is exactly the same as this in terms of how much mass it's seeing or how much it's moving something. It would be exactly the same as me just putting the one, you know, the 2 mass back here again, okay, as me having this mass out here, because I'm moving half the mass twice as much. And that has to be seen as the same as moving 2 mass half as much. And so from this thing's perspective, it can't possibly tell the difference between this and this. How could this possibly know, oh, you know, I'm giving this one twice as much energy? So kinetic, you know, momentum says this will be the same as this. It won't make any difference. Same momentum. Even though this is going half the speed, it's twice the mass, so it's equal. So momentum works perfect. Momentum says, yes, this is perfectly logical. Kinetic energy says there's twice as much energy if I do this, which means somehow you went in with just 1 energies down, and somehow you made 2 going up. And if I do it out here, I can make 3, and then I can make 4. I can, you know, make multiples of the amount of energy just by moving it further down the lever. Making a lighter object further down the lever, I can make multiple increases in my energy. So right here we have free energy. All right, so if you have some idea, okay, that this lever actually works, and that, yes, you'll concede this will leave with twice the velocity, you have to concede that it's a free energy device. And if you're saying it only leaves with 1.4, I mean 0.4 increase, right? So it's only 1.4 to keep the kinetic energy, to conserve kinetic energy. You have to explain, how did the lever know only to give it 1.4? I mean, how did it know to only give 1.4 the velocity? How could it tell the difference between the 2 mass at this location and the 1 mass at this location, when all it can really see is how far am I moving this part of the lever? It's going to move this part of the lever exactly the same amount, whether this is here or whether this is here. This part of the lever is going to move the same exact amount. So how could it possibly tell you put a half mass out further? Yeah, so that's the argument. I mean, the lever, a thousands-of-year-old device, proves the kinetic energy theory can't possibly be correct because it's free energy. You know, it doesn't work. Okay. So I don't know if I'll get a counter argument. There hasn't been anything like a counter argument. Some sort of explanation. Either you have to say that levers don't work and it's 1.4, which I don't think you could actually say experimentally that could be shown, that levers fail, you know, that it wouldn't oscillate perfectly well with the half mass over here Okay, and this mass here that I couldn't make the lever oscillate perfectly, and I couldn't make it balance perfectly, when of course you know it would be. And so if it can balance and it can oscillate, you've got to know that it could launch just as easily, and that its launching speed is going to be the same as its oscillation speed. The oscillation speed is twice as high over here as it is over here. So just oscillating, I'm already creating free energy on this side because the object on the scale has twice as much energy by your theory. I mean, there's no way to unravel this into anything else but a whole, how did you make a mistake this egregious? I mean, how can you be so dishonest to sit there and argue that you have an explanation when you don't? All right. So I'll come back with the other momentum type argument. All right, should be back. All right, so on to elastic, inelastic, and superelastic, which would be storage. So we have these different kinds of collisions. So let's say if it's soft thing against soft thing, all right, we have a collision, and we know it doesn't go anywhere, but it could rotate, spin around a lot, and it gets smushed. That is, it gets deformed. So we know that's what happens with soft thing against soft thing. And we have hard thing against hard thing, all right? And we have no problem. This goes this way, this goes this way. They come in this way, and they go out that way, all right? And then you have spring, okay, which will end up with the same result when they're even masses, okay? So if we put a spring in between two even masses, crash them into each other, we'll get the same result as elastic, but it's really spring-tastic. Because if we start changing the masses, that is, we make the masses bigger or smaller, then we'll start getting different answers. So when we did this experiment, I do it with a bigger object, crashing into each other. The fact is, or one of them crashing into one that's not moving. So let's just say one of them's not moving. All right, so let's just eliminate this motion. So this one's standing still, this one we're going to bang into. All right, and the fact is that this experiment will happen. The outcome will be the big object and the small object will be leaving in the same direction. And in this spring case, the little thing will be going that way and the big thing will be going that way. So there won't be the same outcome depending on which one's actually moving. So that's the argument against relativity, that it's not just relative. Because depending on which one's moving, I'll get a different answer. All right, and what the spring is doing is storing the energy. It's absorbing energy, compressing, and then at a later time, it releases it back. And it distributes it. One half goes this way, so to speak, and one half goes this way, like any explosion. It distributes the energy in both directions. So it stores some energy. This one doesn't feel the energy of this coming in because the spring compresses. So it doesn't feel the full impact. And then when the spring re-expands, it gives this one a boost and it gives this one a boost. And that's why you're getting the opposite direction out of the experiment with the superelastic spring, or the storage device. The spring-tastic experiment, where they end up going the same direction until you make this one small enough. So this mass has to be really small for you to get a reflection. So the spring just essentially changes the point at which you get a reflection. So you get a reflection with a big object if you use a spring, and you only get a reflection if you have a tiny object otherwise. So you need to be, it has to be much smaller, like 1/5. There has to be a pretty good disproportion between these two masses before you'll get it reflected, because it won't be able to get enough energy into the big thing because it's all in the form of a high velocity, and the high velocity can't get into the big object. Big objects can't leave fast. They have to leave slow, so you have to put into them slow velocity. So without a conversion device, you could also think of the spring as a converter, because what springs allow you to do is you can compress it really slow. I could take 1 day to compress a spring this much. I could take a whole day, right? So I'm really slowly compressing it, or I can compress it in 1/10 of a second. 1/10 of a second. I could compress it. And the fact is, it stored the energy just fine. and now it will release it at any speed you want to. So you put a big object on it, it'll release the energy slowly. Put a light object on it, it'll release the energy quickly, high velocity. So it can give you any velocity depending on what mass you put on it. So it's essentially a converting device. So unlike these collisions that can't do conversion, the spring can. And that's so part of the energy you're converting into something that can give the energy to both objects at the speed they want. It can give the big object a slow velocity, a small v. It can give the big object, a small object, a big v. So it can apportion the energy at any velocity, which is important to understand. So back to the, so we can conserve the energy. All of this stuff, momentum works in all of these experiments. You're not going to show me an experiment where momentum fails except for the Professor Lewin one, right? So we have pretty consistent results in terms of momentum being conserved. You can just add up this way plus this way, okay? You don't subtract. There's no minusing, okay? So that's just crap. That only works inside your spaceship. That doesn't work when you're shooting this stuff outside your spaceship. So you can't make the argument, I sent 30 this way and I sent 130 that way, but I only had to use 100 joules of fuel. You can logically know that can't be possible. You can't use 100 joules of fuel and then create 30 joules going out that way and 130 going out that way and say somehow the 30s canceled each other and it's only 100. It isn't only 100 in the real universe, and it's just nonsense to say you can do that. It's obviously gingerbread talk. It's you know it's a fairy tale. Anyway, all right. So the clay, you can understand where the energy goes, right? The energy comes in, and the object actually, the little atoms start going in all kinds of wrong directions. So you can see this a little bit in a ballistic pendulum, actually. They're not that perfect. That's why they don't use them anymore, frankly. I mean, to measure the energy of a bullet. Is because, when the bullet goes in, it does cause a lot of clay to move in these directions. And you never get that energy back in terms of a velocity this way. It always degrades what you're measuring as a velocity, but some of the energy is going to go in directions. Some of the clay is going to push out of the thing, Lots of stuff is going to be moving in directions that won't have anything to do with measuring the direction of your velocity. So it's only the bits that you push in this direction that you're going to be able to measure. So only bits of clay that are still moving in the same direction as the bullet will be the ones where the friction will add up to your velocity. But the friction that goes in the wrong directions, you're not going to get that back. It's not going to turn around and go back this way again. So that is lost as heat and deformation, the movement of atoms from one place to another. And that's what happens in the clay. You move a bunch of clay atoms, and by moving them, they're still moving, but what are they slowed down by? Oh, the atmospheric pressure, the stickiness with each other. They transfer their energy to each other, and so it moves more clay and moves more clay and more clay. And so when you add it all up, it's going to be a heat signature. That's going to be all your energy. All your energy is going to be essentially converted into heat, because all the deformation doesn't mean anything except for the heat it creates. That is, except for how much it disturbs the environment, the atmosphere. So it's pushing into the atmosphere. Moving air molecules is where all your losses are going to be eventually. And you're going to also thermodynamically produce a bunch of infrared radiation and other stuff that's, from the heat. That's going to create a bunch of little sparks coming off, so to speak. You think of them little sparks. So you're going to just lose all the energy to the atmosphere as friction with the atmosphere. But you know it's there. So Leibniz, Descartes, Galileo, and Newton all knew that. They all argued for, yeah, okay, with soft objects, all you're doing is transferring a very straight momentum into momentum in all kinds of little directions. You're taking momentum of one big object and you're converting it into the momentum of a bunch of little objects. And if you add up all the momenta of all the little objects and all the friction that slowed them down, if you add up all that, it'll equal what this was. You'll get back your energy. So it's just, in one form, you convert it into friction. So you can think of the two pieces of clay hitting each other as all the energy just gets absorbed as energy going in wrong directions. Okay, neither this direction nor that direction. It ends up going this way and that way, almost like a water wave, where the energy this way is converted into energy up, and then gravity converts it back into energy down, And then the water pushes, because there's more pressure on one side than the other, it ends up converting into motion that way. So it's, the motion starts this way, it goes up, it goes back down, and then it goes this way. That's all that's happening with an ocean wave. And this is the energy getting destroyed, essentially by being destroyed by taking new paths with new objects. So the energy didn't go away, it just got used up in a bunch of friction. And all of these things will end in friction. They'll all be degraded eventually. They'll be slowed down by creating energy in the ground and energy here and energy there with all the friction. So the ideal is to get rid of as much of the friction as possible. But that's all it is. It's just motion of big things converted into motion of little things. And then little things can give motion to big things. But that's the conservation, and momentum always gets right answers. Kinetic energy almost always gets wrong answers. And this really shouldn't be argued by reasonable people. And I've received no reasonable counter-argument. So anyway, we'll call that enough of a video, I think. I think so. I'll think about it and see if there's anything I have to throw in, but I don't think there will be. Alright, so that probably is enough. So in summation, we're still just waiting on evidence. You can't really have an argument when there isn't evidence on tables to argue the evidence. We're trying to decide guilt or innocence, and we have to do it in an atmosphere of depraved, vacant evidence. Now I would argue it's the prosecution, the established science has some obligation to have evidence. They have a zillion air tracks, and they have all the equipment and all the money and all the rest of it, and they should be able to produce some evidence. So when they say an 8-pound bowling ball going twice as fast as a 16-pound bowling ball has twice as much energy, they ought to have an experiment proving it or showing it. If they say a 10-ton train going 5 miles an hour is half as energetic as a 5-ton train going 10 miles an hour, then they should have a piece of evidence to show it. They should show this physics to be true. They shouldn't be just saying it to be true. If it takes 4 times more gas to go twice as fast in a car, I mean, this is an experiment they could have done in the last 150 years. Why haven't they done it? Well, 138 years. Why don't we have these experiments? So they have some obligation. The prosecution showing up, it's making accusations, it's making statements. The defense attorney really shouldn't have to produce any evidence if the prosecution has done its job, and they just haven't. So they haven't produced any of this 4 times more fuel argument. They haven't produced this, it has twice as much energy. They haven't shown the lever conserving kinetic energy, because it won't conserve kinetic energy. It overtly makes free energy. And they have no explanation for why we don't have free energy levers in our yard. They'll say, well, because we're idiots. We didn't take advantage of modern physics, because modern physics says all you need is a lever and you got free energy. Just drop a 10-pound thing and you'll get twice as much of the energy it took you to lift the 10 pounds. You'll get twice as much, or 3 times as much, or 4 times. If you can make a long enough lever, you can get an awful lot of energy for free. So they have some obligation to show it. They won't show it, and so there's just a stalemate of argument. So I'm just waiting. We'll see if the physicist guy that Toady knew, we'll see if he responds with anything, and if not, I don't know where it goes from here. I mean, I would like some real physicist to make an argument, make a point, and show some evidence, but nobody can do that. So until somebody produces something for me to debate, there's nothing really to debate. I'll make my assertions that this is how it will come out, that levers do work exactly as I've experienced them to work. Okay, they don't make energy. They just redistribute energy, and that's all they can do. A lever can't make more kinetic energy on one end than that's on the other end. Can't do it. It doesn't happen because there is no kinetic energy. It's just a nonsense. So anyway, till the next time, and such, and so forth and whatnot. This has been DraftPhysics.com and DebatePhysics.com also. Video presentation to a really dumb wind. Yeah, it's the wind, but it's really dirty and stupid. That's all there is. Yeah. So, until something else shows up, until something else blows by, stalemate and such.